In this video, we're going to talk about detour proofs. In a detour proof, it might be necessary to prove that more than two sets of triangles are congruent. So this example will illustrate that. So let's call this point A, B, C, D, and E. So let's say that we're given that AB is congruent to CB, and that AD is congruent to CD. Go ahead and prove that AE is congruent to CE. So let's make a two-column proof with statements on the left side and reasons on the right side. So let's start with the first statement, that AB is congruent to CB. So we're given that statement, and let's mark the diagram. So this is AB, this is CB. Our goal is to prove that AE is equal to EC. So in order to do that, we either have to prove that these two triangles are the same, or if we could show that this triangle is congruent to this one, then we could prove that AE is equal to EC. Now we have the second statement, that AD is congruent to CD, and that's given as well. So let's mark that too. Now notice that we can prove that this triangle BAD, is congruent to BCD, because we already have two sides of that triangle, and also we have the common side. So in the third step, we can say that DB is congruent to itself based on the reflexive property. So let's mark that. So in step 4, we could say that triangle, I might need more space. Let's put this over here. So triangle BAD is congruent to triangle BCD. And this is based on the SSS postulate. And we've used the first three statements to prove that those two triangles are congruent. So now, it might be easy to focus on this triangle. I'm going to focus on these two. If I can prove that those two triangles are congruent, then I can show that AE is congruent to EC. So what should we do at this point? So we already know that AD is equal to CD, and we also have a common side. So we just need one piece of information, one more extra piece that can help us to figure this out. Now, because triangle BAD and BCD are congruent, then we could say that this angle is congruent to that angle, and that angle is a part of the large triangle. So let's say that triangle, or rather angle, ADB is congruent to angle CDB, and we could use CPCTC. Corresponding parts of congruent triangles are congruent. So now we have enough information to say that this triangle is equal to that one. But there's only one other thing we need to do. We need to say that AE is congruent to itself based on the reflexive property. So we don't have to remark this symbol. So now, in step 7, we could say that triangle ADE is congruent to triangle CDE. And the reason for that is we have a side, an angle, and a side. So it's based on the SAS postulate. And so for this side, it's based on statement 2, AD equals CD. And for the angle, it's based on statement 7, ADE equals, actually not statement 7, statement 5, ADB equals CDB. And for this side, we've used the reflexive property of step 6. So we could say it's based on statements 2, 5, and 6. So now that we've proven that triangle ADE is congruent to triangle CDE, we can now make the last statement that AE is congruent to CE. And the reason, CPCTC, corresponding parts of congruent triangles are congruent. So this is a detour proof. And as you could see, we had to prove that 2 sets of triangles were congruent in steps 4 and 7. And that's the basic idea of a detour proof. So everything you've learned before still applies here. It's just there's a lot more work. So make sure you know the postulates for triangle congruence. Now let's try another example. Let's say this is A, B, C, D, E, and F on the inside. And in this problem, you're given that AB is congruent to AC. And you're also given that AD is congruent to AE. And you need to prove that triangle BFC is isosceles. So go ahead and work on this detour proof. So you're going to have to find a way to prove that 2 sets of triangles are congruent. This is going to be a long one, so you want to make sure that you have plenty of space to do this. Feel free to pause the video if you want to try it first before watching the answers. So let's start with the first statement. I'm going to have to try to write small. So we know that AB is congruent to AC. And that's given. So what we know is that this is AB and this is AC. So just keep in mind that they're congruent. Now let's think about what we need to do. We need to prove that triangle BFC is isosceles. In order to do that, we need to prove that these 2 sides are congruent or that these 2 angles are congruent. So how can we do that? Well, we can prove these 2 sides are congruent if we can prove these 2 triangles are congruent. But let's write down what else we have. So we know that AB is equal to AC. And also AD is congruent to AE. So that's another given. So this is AD, that's AE. Now, it might be helpful to draw those two triangles. So what I'm doing is I'm drawing triangle BAE and triangle CAD. So this is A, this is E, and this is B. And here this is A again, that's D, and that's C. So we know that AB is equal to AC, so which means that this side is equal to that side. And we have that AD is congruent to AB. AD is congruent to AE. So this is AE, this is AD. Now, is there something else that we can come up with to prove that these two triangles are congruent? What else do we know? Because we're only given these two statements. Now notice that these two triangles share a common angle. That common angle is angle A. So therefore, in step 3, we could say that angle BAD, not BAD, but BAE rather, that's an E. So that's congruent to angle CAD. And the reason? It's based on the reflexive property. So now we can make the statement that those two triangles are congruent. So we can say that triangle BAE is congruent to triangle CAD. And the reason for that, it's based on, side, angle, side. So it's based on the SAS postulate. And we have to use statements 1, 2, and 3 to come to that conclusion. So now that we've proven that those two triangles are congruent, what else do we need in order to establish that these two triangles are congruent? Well, let's see what we know. We can clearly see that these two angles are congruent. They're vertical angles. And we also know that segment AB is congruent to segment AC. And if AD is congruent to AE, then we could prove that BD and EC are congruent. Now, since we know that this triangle is congruent to that triangle, what we can say is that this angle is congruent to that angle. And so we can prove that this triangle is congruent to the other one based on the angle-side theorem. So let's go ahead and write out the information. So we're going to say that this angle is congruent to that angle. So number 5, angle ABE is congruent to angle C. Actually, I have to fix that. That's going to be congruent to angle ACD. And the reason for that is CPCTC. Corresponding parts of congruent triangles are congruent. So now we can get rid of this stuff. So this angle is congruent to this one. Now we can say that this angle is congruent to this one in step 6. So angle DFB is congruent to angle EFC. And the reason? Vertical angles are congruent. Now, we need to use segment addition to prove that those two sides are congruent. Now let's focus on statement 1. AB is congruent to AC. AB is the sum of AD and BD, and AC is the sum of AE and EC. So what I'm going to do is I'm going to replace AB with the two segments that add up to it. So AB can be replaced with, actually before we do that, we need to make this statement. AB is equal to AC, and that's definition of congruent segments. And now we can perform a mathematical operation with this. So I'm going to replace AB with AD plus BD. So AD plus BD is AD. And now AC, I'm going to replace that with AE plus EC. So this is segment addition. Now in step 9, I'm going to replace AD with AE. AD and AE are congruent. So you could write AD and is equal to AE, definition of congruent segments. And now I'm going to replace AD with AE. So in step 10, I'm substituting AD with AE. So I have AE plus BD is equal to AE plus EC. And that's based on the substitution property. And because these two are the same on both sides, I'm going to subtract both sides by AE. So I'm going to be left with BD is equal to EC. And that's the subtraction property. Now in step 12, I can say that BD is congruent to EC. And that's definition of congruent segments. So now we can put the mark BD is congruent to EC. So now I can say that these two triangles are congruent. So in step 13, we're going to say that triangle DFB is congruent to triangle EFC. And that's based on the angle side theorem, so AAS. So now we got to write the statement numbers. So the first A came from the vertical angle theorem, which is based on statement 6. The second A, let's see where that came from. So that was ABE is congruent to ACD, which is based on statement 5. And then we said that these two sides are congruent based on statement 12. So now that we've proven that these two triangles are the same, we can now make another statement. And that is that, let's use a different color. This side is congruent to that side. I'm going to use 3 marks. So we could say that BF is congruent to CF. And it's based on CPCTC. So now, for the final thing, I can make the statement that triangle BFC is isosceles. So I'm just going to put an arrow because I'm out of space. So this part needs to go here. I'm going to put 15. And the reason for that is if two sides of a triangle are the same, then the triangle is isosceles. So I'm just going to write definition of an isosceles triangle. And so that's it.